Decomposition of rocks and minerals by various chemical processes is called chemical weathering. When a rock is brought to the surface millions or billions of years after it has formed, the original minerals that were crystallized deep in the crust under high pressures and temperatures are unstable in the surface environment and eventually break down. The primary agent in chemical weathering are water, oxygen, and acids. These react with surface rocks to form new minerals that are stable in or in equilibrium with the physical and chemical conditions present at the Earth's surface. Any excess ions left over from the chemical reactions are carried away in the acidic water. For example, feldspar minerals will wither to clay minerals, releasing silica, potassium, hydrogen, sodium, and calcium. These elements remain in solution and are commonly found in surface water and groundwater. Newly deposited sediments are often cemented by calcite or quartz that is precipitated between the sediment grains from calcium and silica bearing water respectively. Feldspar plus water is equal to clay mineral plus soluble cations and anions. The effectiveness of chemical weathering is closely related to the mineral composition of rocks. For example, quartz responds far slowly to the chemical attack than olivine or pyroxene. Agents involved in chemical weathering. Water. Water is the main agent of chemical weathering. Although water in pure form is inactive, it becomes a powerful chemical agent when a small amount of oxygen and carbon dioxide are dissolved in it. Rainwater usually contains these gases. Water is a polar molecule which moves by capillarity, can get drawn into rocks, forms weak bonds with unsatisfied ions, releases a hydrogen ion which are small and capable of penetrating a mineral structure, carries chemically active ions that attach to rock. Acids. Acids are chemical compounds that decompose in water to release hydrogen atoms. Hydrogen atoms frequently substitute for other elements in mineral structures, breaking them down to form new minerals that contain the hydrogen atoms. The most abundant natural acid is carbonic acid, a weak acid that consists of dissolved carbon dioxide in water. Rainwater usually contains some dissolved carbon dioxide and is slightly acidic. Other acids that can affect the formation of minerals in the near surface weathering environment are organic acids, which are derived from plant and humus material. Strong acids that are naturally occurring in the environment are rare. They include the sulfuric acids and hydrofluoric acids released during volcanic and hot spring activity. Oxygen. Oxygen is present in air and water and is an important part of many chemical reactions. One of the more common and visible chemical weathering reactions is the combination of iron and oxygen to form iron oxide, that is rust. Solution or dissolution refers to the process that places dissolved ions into water and usually carries them away. The loss of some ions, of course, necessarily carries with it a change in mineral content. In some cases, solution acts alone as a chemical weathering agent. More often, it works in concert with other processes. What typically happens to limestone in a wet climate is an excellent example of withering purely by solution. Control of chemical withering. Temperature. Higher temperature, more available energy for reactions. Thus, warmer climates experience more chemical withering. Moisture. Most withering reactions require water as a medium, thus moist environments are favored. pH. Hydrolysis requires hydrogen ions, thus pH, the negative log of hydrogen ion, is a limiting factor for them. Redox potential EH. Just as pH characterizes the transfer of hydrogen ions between reagents, EH describes the likelihood of the gain or loss of electrons. Measured by means of an electrolytic cell containing a reference electrode of known redox potential. A positive value indicates a tendency for oxidation, that is losing electrons. Negative gives a tendency for reduction. Gaining electrons, just as hydrolysis, is limited by the availability of hydrogen ions. Oxidation reactions are limited by the concentration of oxygen. Processes of chemical withering. Oxidation. Oxidation is the reaction of rock minerals with oxygen, thus changing the mineral composition of the rock. In this type of withering, the anion in a mineral is replaced by a more reactive anion called an oxidant. Oxygen itself is the most commonly substituted anion, though others can work under certain conditions. In effect, a mineral is changed into an oxide by this process. Usually the anion being replaced is removed from the system by solution in water. Most oxidation reactions do, in fact, occur faster in the presence of water than they do in its absence. In fact, the water usually introduces the oxygen, which dissolves in it very much as carbon dioxide. The reactions work best on minerals that contain cations from the middle part of the periodic table, where the ions can exist in multiple oxidation states, that is, they can enter into bonds by giving or receiving different numbers of electrons depending upon exact conditions. The oxidation is more active in the presence of moisture and results in hydrated oxides. Mafic minerals such as pyroxenes, amphiboles and olivines contain some iron. During withering, the oxygen unites with iron, producing insoluble iron oxides. Limonite and hematite are very common products of oxidation, which imparts the red and yellow colors to the soils. The following equation explains that how a ferromagnesian mineral reacts with oxygen. 2FeSiO4 plus 3O2 plus H2O will give rise to 2Fe2O3 plus 2SiO4 minus 4 dissolved silica plus H2O. Olivine plus oxygen dissolved in water alters to hematite plus silica dissolved in water. The Fe2O3 produced by these reactions is relatively insoluble and precipitates to form hematite, which is red in color. This gives rise to the characteristic reddish or rust-like colors on the withered surface of Fe-rich rocks. Note that oxidation of Fe in a silicate will take place only after this Fe is released from the silicate structure by hydrolysis. Some other reactions that explain about oxidation are as follow. 4FeO, that is ferrous oxide, plus O2 will give rise to 2Fe2O3, that is ferric oxide, 4Fe3O4, that is magnetite, plus O2, which is going to be converted into hematite, which is 6 2Fe2O3. 2Fe2O3, that is hematite, plus 3H2O will give rise to 2Fe2O3, 3H2O, that is limonite reduction, the process of removal of oxygen, and is the reverse of oxidation, and is equally important in changing soil color to grey, blue or green, as ferric iron is converted to ferrous iron compounds. Under the condition of excess water or waterlogged condition, less or no oxygen reduction takes place. In specific type of environment, such as where the soil is rich in decaying vegetation, minerals and rocks containing iron oxide may undergo a reduction of oxides to elemental iron. In this case, the decaying vegetation supplies a carbonaceous content causing reduction. Hydration. Chemical combination of water molecules with a particular substance or mineral leading to a change in structure. In hydration, the water molecules combine chemically with minerals to produce new compounds. The ions tend to hold the polarized side of the water molecule and form a hydrate. This process in addition of water molecule is termed as hydration. Soil forming minerals in rocks do not contain any water and they undergo hydration when exposed to humid conditions. Upon hydration, there is swelling and increase in volume of minerals. The minerals lose their luster and become soft. It is one of the most common processes in nature and works with secondary minerals such as aluminum oxide and iron oxide minerals and gypsum. A good example of hydration is the absorption of water by anhydrate resulting in the formation of gypsum. Hydration expands volume and also results in rock deformation. CaSO4 plus 2H2O is equal to CaSO4 2H2O, anhydrite gypsum. Another good example for hydrolysis is the conversion of olivine to serpentine. 3MgO FeO SiO2 plus 2H2O is equal to 3MgO 2SiO2 2H2O plus SiO2 plus 3H2O, that is olivine converted to serpentine. Hydrolysis. Hydrolysis is a chemical reaction caused by water, most important process in chemical weathering. It is due to the dissociation of H2O into hydrogen ion and OH ions, which chemically combine with minerals and bring about changes such as exchange decomposition of crystalline structure and formation of new compounds. Water acts as a weak acid on silicate minerals. Water changes the chemical composition and size of minerals in rock, making them less resistant to weathering. When this mineral is completely hydrolyzed, clay minerals and quartz are produced, and such elements as potassium, calcium or sodium are released. For example, a hydrolysis reaction of orthoclase, that is alkali feldspar, a common mineral found in igneous rocks, yields kyanite, silicic acid and potassium. Hydrolysis of silicate minerals. The chemical weathering of the silicates is primarily a process of hydrolysis as illustrated by the oxidation of the olivine mineral forsterite, that is Mg2SiO4 plus 4H2O, 2Mg2 ions plus 4OH1 plus H4SiO4. The role of carbonic acid can be illustrated. Mg2SiO4 plus 4H2CO3 is equal to 2 Mg2 ions plus 4 HCO3 1 minus plus H4SiO4. In the immediate vicinity of sulfide mineral veins where strong acids are being produced, the reaction is Mg2SiO4 plus 4H1 plus is equal to 2 Mg2 plus H4SiO4. The end product of the reaction are two soluble materials, K1 plus and H4SiO4, that are removed in solution, and a solid product, that is the major product of chemical weathering of all common silicate minerals except for the olivine minerals and quartz namely. Clay minerals here represented by the formula for the kaolinite minerals. The olivine minerals are excluded because they do not contain that aluminium required for the formation of nearly all of the clay minerals. The general definition of clay minerals describes them as hydrous aluminium silicates. It was previously shown that the olivine minerals decompose primarily by oxidation. Quartz is excluded primarily because it does not react with either dissolved oxygen, does not oxidize, nor does it react with dissolved carbon dioxide. The fact that it does not react with the two major atmospheric gases involved in chemical weathering explains the durability of quartz at Earth's surface. Because of the variety of cations available in the major silicate minerals, other clay minerals certainly will form depending on the composition of the rock undergoing weathering and the chemical conditions. It is important to note that the above reactions have not been successfully duplicated in the laboratory. It is very possible that carbonic acid is involved and that all of the metals contained within the silicate minerals, with the exception of aluminium, are removed as soluble bicarbonates. Regardless of the details involved in the chemical weathering of the silicate minerals, the hydrolysis of the silicate minerals will always leave the solution more basic than it was in the beginning. Any solution in contact with silicate minerals cannot remain acidic for long, and if contact is maintained for any length of time, the solution must become alkaline. How alkaline the solution will become will depend on the combination of minerals undergoing hydrolysis, but it will commonly be in excess of pH equal to 7, but rarely above a pH equal to 9. Carbonation. It is the process of weathering of rocks under the combined action of atmospheric carbon dioxide and moisture. Carbon dioxide in the atmosphere and in the air trapped within soils is readily absorbed to water to form carbonic acid. Although relatively weak, carbonic acid nevertheless has a pervasive cumulative effect in the chemical weathering of a variety of different kinds of rocks. It is involved in the dissolution of common silicate minerals and is particularly effective in dissolving limestone and dolomites. The silicates of potassium, sodium and calcium are particularly vulnerable to decay under conditions of carbonations. The typical example is that feldspar. Orthoclase, a very common and important constituent of many igneous, sedimentary and metamorphic rocks, which decompose according to the following reaction: 2KlSi3O8 plus 2H2O plus CO2 is equal to Al2Si2O5 OH4 plus K2CO3 plus 4SiO2. Orthoclase plus carbonic acid is equal to kaolinite plus potassium carbonate plus silica. Note that both the potassium ions and the SiO2 can thus be carried in the aqueous solution, leaving behind the clay mineral kaolinite, that is Al2Si2O5OH4. In nature, water usually contains other substances that contribute additional hydrogen ions or which cause the dissociation of H2O to release hydrogen ion. The end products in the above reaction are a clay mineral, a soluble bicarbonate and silica. Further, in the above equation, sodium or calcium may be present instead of potassium if the mineral in the equation is another type of feldspar. The main end product, kaolinite, is formed in all such cases. Only the soluble carbonate differs in accordance with the metallic ions of the feldspar type. This chemical change in the rock produces a definite alteration in the physical constitution of rock. A soft clay mineral is formed in the place of the hard mineral, thereby affecting the strength of the rock very significantly. Carbonates are removed in solutions and silica from colloids. This may result in partial or total conversion of a strong igneous rock like granite into a mass of soft clay like in the zone of withering. The reaction for limestone is H2O plus CO2 is equal to H2CO3 plus water plus carbon dioxide is equal to carbonic acid, H2CO3 plus CaCO3 is equal to CaHCO3 2. Carbonic acid plus calcite is equal to soluble calcium. When the calcite comes in contact with the carbonic acid, the carbonate splits from the calcium Ca++ and combines with the hydrogen ion present in the carbonic acid, forming the free calcium which is soluble in water along with the bicarbonate. In order for carbonation to occur, water must be readily available. For this reason, carbonation is most vigorous in most climates. When minerals containing calcium, magnesium, sodium or potassium react with the carbonic acid, carbonates and bicarbonates are formed. These soluble products are removed by groundwater. The three remaining elements, aluminum, silicon and oxygen, join with water to produce stable clay minerals. Solution process. Some substances present in the rocks are directly soluble in water. The soluble substances are removed by the continuous action of water and the rock no longer remains solid and forms holes, rills or rough surface and ultimately falls into pieces or decomposes. The action is considerably increased when the water is acidified by the dissolution of organic and inorganic acids. The dissolving away of thick beds of salts, halides and gypsum is an example of simple solution withering. NaCl plus H2O is equal to Na plus Cl plus H2O dissolved ions with water. When salts dissolve in water, the NaCl splits into sodium ions and chlorine ions. This is caused due to the breaking of covalent bond. The ability of water to dissolve substance is related to the configuration and electrical properties of the water molecules itself. A water molecule consists of a large, strongly negative oxygen ion and two hydrogen ions. The hydrogen ions have contributed their electrons to the molecule and thus exist as two small positively charged protons. Both of the protons are located on the same side of the molecule so that it has an electrically positive side and electrically negative side. The electrical charges at either end of the water molecule not only attract their opposites in other water molecules, but also attract compounds in rocks and minerals that likewise have separated centers of positive and negative electrical charge. These compounds are taken into solution as weathering proceeds. In our today's lecture, we have studied about disintegration of the rocks, which is known as weathering. Weathering of rocks can be physical, chemical and biological. The primary agents in chemical weathering are water, oxygen and acids. These react with surface rocks to form new minerals that are stable or in equilibrium with the physical and chemical conditions present at the Earth's surface. Chemical weathering is controlled by factors like temperature, moisture, pH and EH. Process of chemical weathering includes oxidation, reduction, hydration and hydrolysis. Study of chemical weathering helps us to understand the surfacial processes. Thank you.